How's it everyone who's watching this? This is my 37th video on my channel, and today we're going to be finishing Intensive Science and Visual Philosophy by Manuel DeLanda. In the last episode, we began Chapter 4, Virtuality and the Laws of Physics, examining the epistemological side of Deleuze's project. In this episode, we'll continue along this path, further connecting it to his ontology. Without further ado, DeLanda begins this half of the chapter by discussing isomorphism, the quality of two or more things of different natures mirroring each other's behavior. These relationships aren't ones of resemblance, no. Rather, as Deleuze says,
there is no analytic resemblance, correspondence, or conformity between the two planes, but their independence does not preclude isomorphism.
What this means is that, despite being completely divergent in kind, different things are able to act in ways that appear the same. The main isomorphism DeLanda wants to focus on is that between the quasi-cause we talked about in the last couple episodes and philosophers. This involves, in his words,
extracting problems from law-expressing prepositions and meshing the problems together to endow them with that autonomy which ensures their irreducibility to their solutions.
Outside of this particular isomorphism, he also wants to examine the relationship between the problems posed as laws by physicists and the problems of a virtual, along with that between experimental practices and intensive processes of individuation. To do this, he says, we always have to keep multiple things in mind. It isn't enough to just look at the laboratory practices of scientists alone. We also have to think about the behavior of the phenomena and equipment that inhabit the laboratory, as well as that of the mathematical models scientists use to interface with the virtual. Above all, though, as he himself states,
the crucial task is to avoid the subordination of problems to solutions brought about by the search for simple linear behavior.
At this point, DeLanda turns to the idea of brute matter, the notion that matter exists as some sort of homogeneous, unorganized, and inert substance that lacks any ability to affect. This position is clearly opposed by Deleuze's project, particularly when looked at through DeLanda's lens of a flat ontology, where everything is seen as an ontological individual in its own right. To explain, important to a flat ontology is the concept of emergent properties. Essentially, wholes are more than their parts. For example, an institution viewed as an individual is more than simply a composite of the people who act as its cells. It has the ability to do things that a single person or random group of people could not do. In the framework of brute matter, on the other hand, it is firmly additive. Things are equal to the sum of their component parts. In both positions, causality is front and center. From an additive perspective, causality is always linear or external, matter always having to be transformed by something else. However, it's a bit more complicated in the other approach. Here, matter is seen to be almost alive. It has the ability to form assemblages of its own, to produce emergent properties. These properties are the direct result of a non-linear causality, where the diverse bonds between parts of a whole come to cause new things to form that extend beyond them themselves. In DeLanda's words,
none of these individuals is ever a passive receptacle for external causal influences, since their internal causal structure always plays a part in determining the final effect.
Going even further, there are two very different models when it comes to the relationship between matter and linear causality, and between matter and non-linear causality. Additivity and the idea of a solely external causality presupposes that matter be obedient to some unchanging essential laws, like what we went over in the last video. However, when it comes to nonlinear causality, as Deleuze says,
the first model leaves many things, active and effective, by the wayside. We must add an entire energetic materiality in movement, carrying singularities.
Virtual components, like the singularities that organize the long-term tendencies of processes, make matter necessarily dynamic. As DeLanda relates, experimental physics is one domain that we can observe such a thing in. In particular, he singles out the work of Ian Hacking as exemplary. In the physicist's eyes, the field has a life of its own, one distinct from theoretical physics. The laboratory phenomena that an experimentalist individuates or singles out, for example, aren't simply byproducts of the application of certain laws. Rather, individuation involves, to borrow Hacking's words, a keen ability to get nature to behave in new ways. Laws are born and laws die, frameworks come and go, but phenomena remain. In this way, we can't simply imagine some sort of simple, linear causal relationship extending from laws to the phenomena they seemingly explain. Moving on now, experimentalists, the procedures they develop to study phenomena, and what they look at itself, form heterogeneous assemblages. In other words, they mesh together, but in such a way that their differences in kind are maintained. In the process, each component stabilizes the other, creating the necessary conditions for scientific knowledge to be developed. In Deleuze's eyes, these assemblages form the epistemological equivalents of the intensive in ontology. To quote from DeLanda,
much as virtual multiplicities, viewed as self-posed ontological problems, depend on intensive assemblages like ecosystems to progressively give rise to ontological solutions, so experimental problems must first be embodied in an intensive assemblage prior to their being solved.
Through the progressive unfolding of such an assemblage, experimentalists are able to differentiate between what is relevant and what isn't to a given problem. In other words, they are able to develop knowledge, accumulating learning. Taking a step back, DeLanda at this point turns his attention to the role of a quasi-cause. He begins with an analysis of state spaces, like the ones that make up Deleuze's ontology, saying that they simply don't capture causal processes themselves. To explain, the ways in which state spaces capture trajectories can sometimes be confused for sketching out causal relationships. This state of a trajectory causes that one, which in turn causes this, and so on and so on. However, this way of thinking is fundamentally mistaken, the simple reason being that only actual conditions can be considered causes, not the virtual models developed in the state space. Instead, all the information that we can gather is only quasi-causal. To borrow Deleuze's words again,
beneath the general operation of laws, there always remains the play of singularities.
State spaces show us the virtual singularities or attractors that organize their trajectories, not actual causes. To expand on why this approach is so unique, DeLanda turns to comparing Deleuze's ontology to those of analytic philosophers who make use of similar ways of modeling. In particular, DeLanda singles out theorists who focus exclusively on the epistemological role of trajectories. Those who take this approach first measure properties of a real system and develop a curve based on them. Then, in DeLanda's words,
if a system starts its evolution in the same initial conditions as the model, then this curve and the corresponding state space trajectory should be geometrically similar.
Immediately this, particularly the focus on geometric similarity, should ring some warning bells. Deleuze, as we've seen again and again, is adamant in his topological approach. For him, the epistemological value of state spaces lies in their ability to reveal isomorphisms between their topological elements and those of real systems, and the process unveiling singularities and the fact that they are co-actualizations of the same multiplicities. This isn't to say that there can't be similarities between a trajectory and a plotted curve, only that the reason why they are similar is because they share the same distribution of singularities. In this way, another difference between the Deleuzian and analytic approaches rears its head. Whilst the latter is focused almost exclusively on the starting conditions, and by extension, the first few states, that isn't true to the former. The beginning doesn't really matter, since the long-term tendencies of a system, the singularities, will eventually take shape out of the woodwork. For DeLanda, the analytic approach is essentially one of subordinating problems to their solutions, and it's this they would like to end the book on. In particular, he seeks to analyze two instances in the history of mathematics where the aforementioned subordination was inverted. He begins the section by saying,
to Deleuze, mathematical problems are subordinated to their solutions whenever the well-posedness of a problem is approached in terms of its solvability.
An inversion of a subordination thus involves the solvability becoming a consequence, not the cause of, a well-posed problem. To give some context to what he will be discussing, DeLanda now turns to a rough explanation of the question of solvability as it relates to algebra. Essentially, there are two kinds of solutions to algebraic equations, particular ones and general ones. The first concerns the specific numerical values attached to x or y or what have you. For example, the particular solution of x squared plus 3x minus 4 equals 0 is x equals 1. The second category of solutions, those that are general, are, as the name suggests, much broader. To quote DeLanda yet again,
it does not yield any specific value or set of values, but rather the global pattern of all particular solutions. This general pattern is typically given by another equation or a formula.
Using the same example of a quadratic equation, its general pattern can be seen in this diagram. The reason why DeLanda brings up this distinction is to explain what mathematicians generally focus on, the general rather than the particular. When they talk about solvability, it's the exact values they're looking for, in other words, something greater than simple numerical values. In DeLanda's eyes, though, this approach can often be problematic. This is because the focus often falls on trying to find exact solutions for every problem, subordinating the problem under the solution by defining its well-posedness based on whether or not it's nice and clean. This takes us to the first moment of inversion, born out of the difficulties associated with finding a general solution to problems involving unknown variables raised to the fifth power. It was all well and good finding solutions to those variables raised to the second, third, or fourth power, but anything further just didn't comply with the mathematician's methods. The immediate question that was raised was whether or not the problem itself was flawed. As DeLanda says,
was this lack of exact solvability indicative that there was something wrong with the problem as it was posed by the fifth-degree equation?
It was only a few centuries after the problem was discovered that the question was answered. Évariste Galois, the father of group theory that we first looked at in the first episode of the series, found that equations that can be answered with a similar formula form a group of a particular kind. The problem with the problem, as it were, was that it looked through the lens of a wrong type of group. Variables to the fifth degree weren't of the same kind as those to the second, third, or fourth. The main merit in Galois' work, at least for sure, is that he showed the well-posedness of problems doesn't follow from their ability to be solved, but rather the solvability of a problem is a direct result of the problem's form. In other words, the problem itself is primary. Additionally, his approach relied on a similar series of symmetry-breaking cascades as the ones that structure multiplicities and their actualizations. To solve problems, groups were specified into subgroups that could then be specified again. In the process, the specification of problems gave rise to singular solutions. Moving on to the second inversion, DeLanda looks to differential equations. Although calculus is very different from algebra, problems in the field also have general and particular solutions, produced through integration. However, main differential equations can't be exactly solved in a general fashion. In DeLanda's words,
today, we get around this limitation by using computers to generate a population of many numerical solutions, a population which may be used to discover the general pattern.
Yet, when the field was first getting started, this obviously wasn't available to the mathematicians studying differential equations. The result was that many equations that were unable to be solved exactly were left to the wayside. Solvability became the determining factor whether or not a problem was worth looking into. Although we can't really blame the early physicists and mathematicians who fell victim to this phenomenon, solvability radically influenced their worldview. Linear equations, those with one answer, became their almost sole focus, non-linear ones forcibly being made to fit into their narrow framework, for example, being restricted to only very low intensities. However, everything changed with Henri Poincaré, who, similar to Galois, radically inverted the problem-solution relationship, taking a topological approach to calculus. Instead of looking at singular points and trying to solve problems from there, he instead focused on the distribution of singularities themselves, seeking the underlying structures that organize the space of solutions. To borrow from DeLanda,
like Galois, Poincaré bypassed exact solvability as a way to get global information and instead used a novel method to investigate the space defining the problem itself.
Wrapping up this chapter, DeLanda says that much of what he has used to characterize the virtual and problematic in this book is indebted to Poincaré's work, in particular his approach to state space. However, it's important not to forget Galois, whose work on group theory forms the backbone of Deleuze's understanding of symmetry-breaking cascades. In both cases, inverting the subordination of problems to solutions is necessary to a theory of virtuality. To ignore the problematic is essentially to act as if the actual world is all there is to explain. Moving on, the ontology that DeLanda has developed throughout this book is fundamentally historical. Unlike linear models beholden to abstract unchanging laws, it fully accounts for the nonlinear nature of reality. It's dynamic, not static. There's a difference, though, between the historicity of a virtual world and that of the actual world. As we saw a couple of episodes ago, the two had their own temporality, the infinitely future and past ion and the cyclically present chronos, connected to the virtual and actual respectively. These two histories are in constant communication, constant interaction, albeit in often abstract ways. Concluding the entire book, DeLanda quotes Deleuze himself.
It is correct to represent a double series of events which develop in two planes, echoing without resembling each other. Real events on the level of the engendered solutions, and ideal events embedded in the conditions of the problem, like the acts, or rather, the dreams of the gods who double our history.
It's with this that we finish our series on intensive science and virtual philosophy, understanding the relationship between the virtual and the actual. I truly hope you enjoyed or learned something. If you feel I got anything wrong, please do feel free to let me know in the comments so I can do better. Next time, we'll be doing something a bit different than usual, but until then, bye!